You know when you're on a video call and it's just perfectly clear? Or you think about a signal from a satellite millions of miles away, reaching us without being a garbled mess? Well, have you ever wondered how that actually works? It's all thanks to some hidden technology that's constantly protecting our data. So today, we're going to pull back that curtain and look at these unseen protectors of our digital world. I mean, really think about it for a second. When you're streaming something, that data is traveling through the air, through cables. It's bouncing off satellites. It's a really chaotic journey. So why on earth isn't the final result just a flickering wall of static? How does the message actually survive that trip? Well, the villain in this whole story is something engineers call noise. And it's not just, sound. Noise is pretty much any interference out there. Could be a solar flare, could be your microwave oven, anything that can flip a digital 1 into a 0 and completely corrupt the data you're trying to get. It is a constant battle, 24/7. So, living in this world that's just full of digital noise, our information basically needs a bodyguard. The real question is, how do you build one? How do we fight back and make sure that message gets through completely intact? The solution is actually brilliantly clever. Instead of just, sending the data and hoping for the best, we send it with this kind of protective layer. We use a special class of messengers called error-correcting codes. And their job isn't just to detect errors from noise, but to actually fix them on the other end. Okay, but not all codes are created equal. For something like a live broadcast or phone call, data that's streaming continuously, we need a very special kind of hero. So let's introduce the star of our show today, the convolutional code. So what is it? A convolutional code is a type of error-correcting code built specifically for data that flows, not data that comes in neat little packages. And the key phrase here, the real secret to its power, is that it adds its protection based on past information. And this is where things get really interesting. See, on one hand, you have what are called block codes. Think of those like sending a series of postcards. Each one is its own separate fixed-size message. But convolutional codes, they're totally different. They're more like a continuous phone conversation, where what's being said now is directly connected to what was just said a moment ago. And that connection, that's their superpower. Unlike those block codes, convolutional codes have memory. And believe me, this is the entire game changer. It's what lets them weave this incredibly robust and intricate web of protection around our data as it flows. So, the big question is, how does this memory thing actually work? Well, it's a pretty simple and elegant process. As a new bit of data comes in, the encoder doesn't just look at that one bit by itself. No, it looks back at the few bits that came right before it. Then, it uses that entire context, the present and the recent past, to create a brand new protected output symbol. Now, this memory system isn't random at all. It follows very, very strict rules. And because of that, the code creates a predictable structure, not just a stream of random noise. And you know what? Anything that's predictable, well, it can be mapped. And that leads us to this really beautiful visualization called a trellis diagram. A trellis diagram is, for all intents and purposes, the code's roadmap. It shows every single possible path that a valid, correctly encoded message could ever take from one moment to the next. Every twist, every turn, it's all laid out right there in this structure. The blueprint analogy here is just perfect. It's more than a map. It's like the master blueprint for every single valid message. If a received message doesn't follow a path on this blueprint, we know instantly that noise has corrupted it somewhere along its journey. Okay, so we have our hero code that creates this protective layer, and we have the blueprint of all of its possible right moves. But how do we actually use that blueprint to fix a corrupted message? Well, we need a brilliant ally, an expert navigator that knows how to read the map. And the arrival of that navigator changed everything. The source material really highlights this. The widespread practical use of these codes was really only made possible by one specific invention, the Viterbi decoding algorithm. It was the absolute missing piece of the puzzle. The Viterbi algorithm is just a stroke of genius. What it does is it takes the noisy, corrupted message we received and it compares it against that perfect blueprint, the trellis diagram. It then calculates the most likely path through that trellis that the original message would have taken. It finds the best fit, and in doing so, it corrects the errors. Now, what makes it so incredibly effective is that it uses something called soft decision decoding. A simpler decoder just sees a corrupted bit and has to guess. Is it a 0 or a 1? But Viterbi, it can look at the raw signal and say, this looks like a 0, but I'm only about 60% sure. This other one, though, looks like a 1, and I'm 99% sure. Using that level of certainty makes its pathfinding unbelievably accurate.
So now, let's tie all of these pieces together. We've got the code, we've got the map, and we've got the expert navigator. How does this amazing team work together to protect our data every single second of every day?
This table really sums it up perfectly. The convolutional code adds that memory, kind of like a storyteller adding clues based on the words that came before. The trellis diagram? Well, that's the map of every possible valid story. And the Viterbi algorithm? That's our expert navigator, the one who can look at a garbled mess of a message and find the one true path on that map.
And this powerful trio, the code, the trellis, and the algorithm, it's working right now, silently, in the background, in your phone, in your Wi-Fi router, in satellites orbiting the Earth. It is a fundamental cornerstone of the reliable digital world we so often just take for granted.
And that really just leaves us with a final thought. Our world is only getting more crowded, more connected, and a lot more digitally noisy. That fundamental battle between the message and the noise, it's just going to continue. So the real question is, how will our codes, our unseen protectors, have to evolve next?